Okay, my name is Roger Pielke Sr. I was professor at Colorado State University in Atmospheric Sciences, and I'm currently working part-time as senior scientist at the University of Colorado Boulder. And what I want to talk to you about today is the human role within the climate system. And I think I'm going to be giving you a perspective that you don't often see, and hopefully it'll get you thinking a little bit more broadly about this issue. Next slide. Some of the questions that I will try to answer is like, what is climate and what is climate change? Next slide. The climate system is easiest to define and most robustly defined as an interaction between the atmosphere, the oceans, the ice, and it's a chemical, biological, and physical system. And the traditional definition of climate, of course, in weather is it's just long-term weather statistics, but in reality, the climate system is much more than that. So climate is this, then climate change is an alteration of any of the components, either external, such as solar or from volcanoes, or due to human activities, which I'll talk about in a few minutes. Next slide, please. Well, everyone knows about CO2 and other greenhouse gases affecting the climate system, and this is an extraction of the figure of radio forcing change between 2019 and 1750. And I want to point out this is not really the current forcing. This is just a difference in forcing that they estimate between the two time periods. And you can see that carbon dioxide is the largest contributor, with methane second. There are some negative contributions such as SO2, which converts to sulfates, which is actually a cooling effect. But this is the IPCC's summary of what the CO2 and other greenhouse gases and other forcings are in terms of the global average forcing. Next slide. But there's other climate forcings which have gotten much less attention. And these forcings are, I think, underestimated because on a global average, they may actually come out to be of a zero temperature effect, for example, but they can have an enormous effect on circulation patterns, such as, for example, like we see with an El Nino. You have an ocean surface temperature that's warmed. It's over a limited geographical area, but it has global consequences. Therefore, if we have aerosols we put in the atmosphere or land use change that has regional impacts on, for example, the diabatic heating of the atmosphere, we should expect similar large effects, but this has not been properly explored. Next slide. Now I'm going to go through these pretty quickly. These are just examples. This is often shown to say this is the fossil fuel emissions of carbon dioxide in the atmosphere. Of course, everybody in this audience knows you don't see the carbon dioxide in here. This is probably could be water droplets, or it could, and certainly some particulates, carbon, and so forth. So there's emissions cause other things besides emitting CO2. Next one. A topic I done a lot of research on is land use change, and this is just going to show a couple of examples. This is pivot irrigation in the Great Plains of the United States, and you notice darker areas, lighter areas. So there's different absorption of solar energy. There's also different rate of transpiration fluxes. Where it's irrigated, you'll have water vapor fluxes into the atmosphere, and where maybe dry soils, you'll have very little. Next one. And even in an area that we consider pretty rural, there's large changes. This is an area that's been deforested and converted into pasture. And you can see differences in the reflectance, the surface albedo. You'll have differences of heat flux and moisture flux. Next slide. And so we can summarize this in this little figure for an area in eastern Nebraska where we had a field campaign. On the right, you can see an area that's not irrigated. You have a deeper boundary layer. The cloud base is higher. You have lower latent heat fluxes, higher sensible heat fluxes, so the surface temperature would be higher during the day. Where on the left side, you have an irrigated area where the lifting condensation level, which is cloud base, is lower, and you have a greater flux of water vapor into the atmosphere. And we've shown in our research, and I don't have time to go into it here, that this has demonstrably significant effects on the climate, the weather in this type of an area. Next slide. Here's an example for Florida. I did a lot of work on Florida. This shows you on the right side of the figure is an urban area. In the middle is a natural area where it's a sawgrass marsh, and on the left side is agriculture. And there's a large effect from this on South Florida climate, Central Florida climate, because you have converted a natural landscape, which has a lot of water vapor flux from these marshes and swamps, and you've converted it to urban areas, which has less. You've changed the reflectance. And we, for example, have shown that there's been a warming effect in the summer exclusively due to this land use change. Next slide. This just shows the map of how things have changed in Florida. On the left side is the landscape from pre-conversion and development, like around 1900. On the right, this was actually the early 1990s, but not much has changed, except for Everglades National Park in the lower southwest of the figure. You can see the whole area has been converted. And so it should come as no surprise that this has large effects on the weather and the climate and climate change in Florida, irrespective of other human impacts. Next slide. And this is what I consider one of my really good examples of showing this. This is a model simulation in the Great Plains of the United States, Texas, Oklahoma area. And in the lower figure is a model run with the natural landscape, which is shortgrass prairie. And thunderstorms form along a boundary between drier air to the west and humid air to the east. This is how we had all those tornadoes recently. It was formed on this kind of a boundary and moved east. Well, if you take that landscape for a given day and you replace it with what the landscape actually is there now, there's much more water vapor flux because of irrigation, and the crops are planted there. And the model produced a thunderstorm, a severe thunderstorm actually. And that thunderstorm was actually observed. So in this example, it's shown that you can have enormous impacts on your weather and climate just by changing the landscape. Next slide. And so one of the conclusions we've come to is that when we talk about climate, we're really talking about ecology. And the only difference is in the physical sciences, we call it climate. In the biological climate, we call it ecology. But they are identical. They're the same biogeophysical system, same chemical system, and it's true on all spatial scales. And we have some papers on that. And at the very end of my talk, I'm not going to talk about the papers, but I have a list of a number of papers that expand on this topic. Next one, please. Well, here's an example of a model study that came out fairly recently, looked at the biogeochemical effect of added CO2. And what you see in this figure is green areas that have significantly greened up, 25% between 2015 and 1982. This has enormous effects, not only on the carbon budget, for example, which is, it takes up carbon, but it affects how the albedo of the surface, how much energy is reflected into space. It affects the water vapor flux into the atmosphere, and it's over an enormous area. And so this effect has only recently been started to be explored, but again, very inadequately explored. Next slide. Well, part of the confusion, I think, of why this topic's become, first of all, polarized and why it's tended to focus in a too limited fashion is that the United Nations Framework Convention on Climate Change and the IPCC, the International Panel on Climate Change, have two conflicting goals. The next slide. First of all, I'm going to frame it. We've all heard about the apocalyptic over-the-top messaging, and I'm going to give one example following this, but in the news every day. And secondly, we have to recognize human-caused climate change is real and is a serious issue, and this includes the effects from carbon dioxide being emitted to the atmosphere. But that doesn't mean we should overstate the issue. In fact, by doing that, I think we compromise effective policy decisions. The next slide. Well, here's just an example. This came out, I don't know, recently, within the last year. So the tree line is out of control, how the climate crisis is turning the Arctic green. Well, in the paper or the study, you look at it and it says they're creeping north at 40 to 50 meters per year. That's 5 kilometers in 100 years. So even internal to these studies, there's a conflict in terms of what actually is occurring. Next slide. Well, here's what the UN United Nations Framework on Climate Change says, and I just look at the boldface part. Their goal is the stabilization of greenhouse gas concentration in the atmosphere at a level that would prevent dangerous anthropogenic interference with the climate system. Next slide. And so they define climate change as just due to changes in human activity that alters the composition of the global atmosphere. So that's why the focus has tended to be on CO2 and methane and other greenhouse gases. Next slide. But the IPCC has a broader definition. Climate change may be due to natural internal processes or external forces, or to persistent anthropogenic changes in the composition of the atmosphere or in land use. Next slide. So the IPCC then, every few years, and one just came out fairly recently, they have a structure that defines all the things we're hearing about in the news, basically. Working group one is called the physical science basis of climate change. Well, hopefully already you've seen that climate change is not just a physical system. So there's a problem with their framing of it. But everything following that is a derivative. Working group two, which is impacts, working group three, which is mitigation, and all the syntheses reports are derivatives of that first report. But another problem with the first report, it focuses on the United Nations Framework Convention on Climate Change, not really the IPCC mission, which it's supposed to do. Next slide. In fact, you can really frame this as two hypotheses for the IPCC versus the United Nations Framework on Climate Change. The first hypothesis is all the natural causes of climate variations and changes are undoubtedly important. The human influences are significant, involve a diverse range of first-order climate forcings, including but not limited to the human input of carbon dioxide, CO2. This should be the focus of the IPCC report, of course, but it's not. Rather, they take hypothesis two, although the natural causes of climate variations and changes are undoubtedly important, the human influences are significant and are dominated by the emissions into the atmosphere of greenhouse gases, the most important of which is CO2. So there are two framings, two very different policy responses, and hopefully I've given you some thought that maybe hypothesis A is actually the correct one, and that the IPCC has been very incomplete. Next slide. So there's some major unresolved issues. First of all, as I've been talking about, IPCC has not considered all first-order climate forcings. So this is true. There was a National Academy of Sciences report in 2005, which I participated in. It's basically been ignored. It's now, almost 18 years old now. It's just as true today. But what we concluded in that report is that we need to look at other forcings, in addition to CO2, as to how they alter regional and global climate. Because after all, it's the regions that affect our weather. Again, an El Nino, it's a regional forcing with global consequences. And some of these, I've talked about land use change and land management. There's aerosol deposition, for example, nitrogen deposition or black carbon. There's aerosol effects on clouds and precipitation, the so-called microphysical effect, and the biogeographical effects of CO2, and of course, other effects too, of nitrogen and so forth. These have been inadequately explored. Next one. Okay, the second one is global climate models cannot accurately predict changes in regional climate statistics when tested in hindcast runs. What this really means in shorthand is that the regional predictions that are being used in Pennsylvania and elsewhere have no basis in robustness. They're not robust. In fact, you can actually find this conclusion. I've talked about it, and I have a reference there for myself, but more importantly, the previous IPCC report, Working Group 1 in 2013, and Chapter 11 has the statement, these results show that in general, the coupled model, the CMIP5 ensemble, these are the computer climate models that give you their projections out to 2100 and perhaps beyond. They cannot be taken as a reliable regional probability forecast, but that the true uncertainty can be larger than the model spread indicated in the maps in this chapter at Annex 1. What that basically says is all the maps that are in the IPCC have no basis in robustness. And I've published a paper that discussed a whole series of papers that shows how limited the skill is when you look at these models in hindcast. Even if they get the global average temperature reasonably well, they cannot replicate major circulation features like ENSO. They can't look at regional trends properly. So it has a lot, significant shortcomings, yet they're being used to define policy. The next slide. And downscaling to regions from global models have no more skill than the parent models. And I'm not going to talk too much about this, but this basically has been a way people have tried to get finer resolution in the regions. And we've published on that. Other people have published on that. You can't do better than with the global models, even though you have better terrain and so forth. If you feed in errors in the lateral boundary conditions of these models, you can't come up with any kind of skill. Next slide. And a significant fraction of IPCC future scenarios are completely implausible. For example, RCP 8.5. And my son, who I'm going to talk a little bit more in a few minutes here, has several papers out there that that shows convincingly that policy right now is being focused primarily on implausibly pessimistic scenarios of the future. Next slide. Now, I'll talk very briefly about climate metrics, just a couple of examples of how things are actually occurring in the climate system, which you may or may not have seen, but certainly is not reported very much in the media. Next slide. This is a study John Christie has done showing how well the models do with respect to observations in the mid-troposphere temperatures in the tropics. And again, I'm not going to go into the figure in any detail. You can see the red line, which is the model, and you can see the reality, which is lower, showing warming, but much more muted than what the models say. And a recent paper came out within this last week that further bolstered this conclusion. So the models, even the global models, have some serious problems. Next slide. This is people talk about hurricanes increasing, and this is from Ryan Maui. If you haven't done it, you should maybe look at some of his Twitter stuff. But this is global major hurricane frequency from 1980 to near the present. And obviously, there's no trend. If there's any trend, it's actually downward. Next slide. This is the major hurricanes as a proportion of total hurricanes. Again, basically, essentially no long-term trend. And this comes out of my son's work on the Honest Broker. And again, I'm going to say it very shortly, say something about that. I would, as a recommended source of information on some of this. But again, no trends. And yet in the media talks about all the hurricanes getting worse. But if you actually go in and look at the data, it doesn't confirm that. Next slide. So this is my son's Substack. And I would urge you to subscribe to that, as he almost daily and he has stuff on his Twitter and weekly has a Substack post. And I've contributed a few articles to there. It basically is trying to frame it so you get all the broader perspective of how the climate issue and policy are really evolving. Next slide. So I'm going to show you a couple from his Substack. This is with heat waves and heat conditions. The climate, and average temperatures have actually increased. I think that's a fairly robust finding, certainly true in Colorado, other than the wintertime. The wintertime hasn't really increased. But if you look at warm spells and you look at heat waves and so forth, the 1930s, for example, really stand out as being a much more extreme event than what we are seeing at present. So the climate changes, always has changed. Humans are impacting it, but it's not the steady increase in heat, or heat waves, steady increase in hurricanes that you see. Next slide. Now, this is looking at the flooding, economic effect of flooding. What you see there is the decrease actually in flooding. And so, again, an example that's sort of counter to what you often see in the media. Next slide. Well, this is from my son's work too, and I think with Richie, looking at the emissions scenario. This is in terms of the issue of how good are the IPCC model predictions if you accept the models as robust, but you are questioning the amount of emission of fossil fuel emissions of CO2 into the atmosphere. So this is global carbon demand. So the models that are used mostly for projections in regions, I don't know if you do it in Pennsylvania or not, but they're based on, for example, the 8.5 scenario that's on the right side of that figure. And you can see reality is in the red and the blue line towards the bottom. Those are where we're at. The models are running with much more coal than is being used. The net result is even if you believe the models as robust, and which I don't, but if you believe they have robust predictive skill, they are saying that the input to the models is completely implausible and erroneous, and therefore the results that come out of these models, even on the global scale, are worthless. And unless you just want to test the model, but they're not really appropriate for policy application. Next one, next slide. So here's another example. This is an area that I've done a lot of work on. It looks at this claim that the cold waves have become more likely over the world as a result of global warming. And you see this every time there's an Arctic outbreak. People say, well, cold waves can be a cause because of global warming. And hopefully this little short summary of my work can convince you that's bogus. Next slide. So the question is, the polar jet changing? The polar jet, of course, moves north in the summer, south in the winter in the northern hemisphere. And in Pennsylvania, for example, when you get the lake effect squalls coming off the lakes, that's because the polar jet has dropped south. You're bringing cold air over the lakes. When you have a warm spell coming up, that's because the jet is pulled north. The next slide, very complicated slide, but I just want you to pay attention to the fact that's the width between these lines. And the fact that the lines from the bottom of the figure to the top, they go from warmer air in the tropics to the cold air over the Arctic. So if you look at these little circular areas, these vortexes over the polar regions, for example, that's the polar vortex, if you want. The area with a really tight lines is the polar jet. So you can see it meanders around the globe. This is the end of January of this year. The next slide shows this for a couple of days ago. And you see the jet has weakened. There's fewer lines, they're not packed as tight. And if you went and looked at temperatures, you would see it's not quite as cold in the Arctic. And this, I should point out, is in the middle of the atmosphere. It's 500 millibars, so it's about 18,000 feet or so. And what you see up here is that the jet weakens. And if we had a summer map, there might be no lines over the United States, for example. And this particular example in Pennsylvania would be quite mild. So it was mild on April 15th. You can just look at this and say Pennsylvania was south of the polar jet. Next slide. And why this is important is because this jet stream, which is indicated by the dashed lines, that's like those contours I had in the last figure, it's that boundary that causes the development of winter storms. So the top figure is there's a stationary front, and in the middle figure, the warm air is starting to go northward. It's overrunning the cold air, and you get those clouds, which is a scalloped area, and behind it, the cold air starts pouring in. And the bottom figure is when the cyclone becomes mature, and the boundaries, you can still see the jet stream, you can see the lines, you can see the fact that the area south of the bottom of the figure, for example, would be in the warm air, but areas north of that in the cloudy area, the scalloped area, would have precipitation, rain or snow. So this is well understood dynamic process. And what it says is, and studies have shown this quantitatively, is that the stronger the temperature gradient, the stronger the winter storms will be. That's why we have stronger storms in the winter time than we do in the summer. Next slide. And this just shows the same figure, except on the right side, it just shows those solid lines where the one that says NVA and PVA and so forth. You can ignore that, but the lines show a buckling of these streamlines, and that's the polar jets bending. And so what we can conclude from this is that in order for winter storms to become weaker, the polar jet must become weaker. So has the polar jet become weaker? Have cold air intrusions become more common because of global warming? Well, let's look at the next slide. This looks at the Arctic temperatures during the year from 1981 to near the present. You can see the seasonal cycle. It's not as cold in the summer as it is in the winter. And there's been slight changes, but you'd be hard pressed to see any significant changes. In fact, some of the coldest temperatures have occurred in the last couple of years. This temperature is a representation of how strong the polar jet is. If the polar jet was weakening and the polar jet supposedly would get wavier, you would see this change, and it has not changed. The next slide shows this even more convincingly. This is the winds at 200 millibars. So basically the height at which you fly a commercial jet airplane. And this is the data going back several decades. And you can see basically, some regional variations, but essentially no change. So the polar jet has not changed. And the significance of this in the next slide is extratropical cyclone intensity, waviness of the polar jet, and Arctic outbreaks have not changed. significantly, and they will not change until you can change ocean sea surface temperatures in the higher latitudes enough that it doesn't get as cold in the winter. And this has not happened as of 2023. And I think this hopefully will refute all the studies that have done, all the studies that have shown the claim in the media that there's been an effect from waviness. Next slide, please. Well, the reality of it is, try to examine the data yourself. When I taught the course in weather and climate, I was trying to have my students look at the data themselves and not believe me, but look at them themselves. Look at glacier changes, look at temperature changes, look at precipitation changes, and you'll find out things are much more nuanced than you otherwise think. Next slide. And then the question is, how should Pennsylvania move forward with respect to threats from changes in climate? So here's my recommendations. If you can move the next slide. First of all, recognize that there's essentially no skill at predicting changes in regional climate statistics for Pennsylvania. What this means is that if you're using, or anyone is using these assessments, these regional change assessments coming out of the IPCC or any other report, it's based on models that most of them have incorrect emissions, so they're wrong even to start with. But if you run these in hindcast, they have no skill at all. And thus what I've been recommending is an adoption of a different approach. And I'll read this. It's a bottom-up resource-based vulnerability assessment of societal and environmentally key resources of water, food, energy, human health and well-being, and ecosystem function. This inclusive bottom-up vulnerability concept requires the determination of the major threats to these resources from climate, but also from other social and environmental issues. After these issues are identified for each resource, the relative risk from natural and human-caused climate change, estimated from global models, historical record, paleo record, worst-case scenarios, can be compared with other environmental risks and social risks in order to adopt the optimal mitigation and adaptation strategies for Pennsylvania. If one assumes that the models give you the future and you base policy based on that, it has no substantive basis in science, in my view. Next slide. Well, this is just an example of how you can frame it. We do it in terms of ecosystem function and energy, water resources, human health, and food. And the next three slides will just summarize a figure that looks like this, but you can see a range of influences on the perimeter, from biodiversity, from weather, from so land management and so forth. And the next slide shows this same framing for water resources and food. And the next slide shows this for energy and for environmental ecosystem well-being. But the bottom line is that the models do not have the skill to give us quantitative skill for predictions on the region, certainly. And therefore, we really need to adopt a broader perspective to assess risks. So my recommendation for the state of Pennsylvania, and for anyone, is that you look at the risks that are faced from social and environmental concerns, fold in the climate issue, and you certainly use the IPCC results, but use the ones that have emissions, at least, that are within the framework of what's plausible in the future, and use that to define policy. So that's sort of my bottom line message. And on the next slide, I want to thank Manny for inviting me to give this talk. And the next two slides are just summaries of papers. Next slide, please. You can't read that, I'm sure, very well from you, but there's several papers that we talk about this in detail. And the next slide is some more references. These will be on my research website if anyone is interested in following up, and are welcome to take questions if you have the time. Thank you very much.